Saxon Advanced Mathematics, Lesson 14. Dun 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 dun. No more fiddly circles and secants and chords like we did yesterday. That geometry lesson is over. We are now moving into what is officially called trigonometry. Okay? We're going to review our old friends, sine, cosine, and tangent. We're going to take it from the top. So you don't have to remember anything from last year. I'm going to review it all for you. And then we're also going to talk about, well, I'm not going to tell you that. Spoilers. There's another section to this, but it all kind of flows naturally. We're talking about trig. Now, let's start over and figure out what these things even are. First thing I need to tell you is that whenever we talk about sine, cosine, and tangent, we are talking about right triangles. Okay? We're going to learn an exception to that, two exceptions to that, later this year. But we will give you the big fat caveat when we get to it. Generally speaking, sine, cosine, and tangent relate to right triangles only. In order to make sense of these things, we have to define the different sides. This side of a right triangle is always called the hypotenuse. It is the side opposite the perfect right angle. It's the side that looks like it's been cut kitty corner, right? But you can tell the hypotenuse because it's opposite the right angle. Now, in order to talk about sine, cosine, and tangent, we have to orient ourselves to either this angle or this angle. Okay, we never look at this one. And generally speaking, we always focus ourselves on the one that is going this way. So in this triangle, this is the angle we would be interested in. This we wouldn't put ourselves floating up here in the air. We stand down here on the ground. Now, from this angle, we would call this leg, these two are both legs, right? Hypotenuse and legs. The leg that is on the far side of the angle that we're standing by, that's called the opposite. And again, these are the names of the sides. This is called the adjacent. Right? Adjacent means next to. So that helps us orient ourselves to the different parts of the triangle. And incidentally, sometimes we'll flip this around and draw the triangle from that direction. And again, we just orient ourselves. Where are we standing? What is the angle we're interested in? That's where we're standing. The opposite's over here. The adjacent's down there. So don't let it blow your mind if the triangle flips. And we'll go back and forth a lot. Now, sine, cosine, and tangent are simply ratios of these different sides in different combinations. So we abbreviate everything: sine, cosine, and tangent. We don't say sin, cos, tan. We say sine, cosine, and tangent, even when we use the abbreviation. Sine is a ratio built out of the opposite side, the length of the opposite side, over the length of the hypotenuse. I'll write it all out for you because I go the extra mile. All right. The cosine is a ratio built out of the adjacent over the hypotenuse. And the tangent is built out of the opposite over the adjacent. Okay, so we're just mixing up the three different sides. We're just mixing them into different combinations, right? That's all that these signs are. For a certain size angle, the ratio of one side to the other side is always the same. If you take into account the angle size, this ratio will be the same for any angle of that size. That's kind of weird that we think about that. but they always will form, these pairs of points will form a decimal number, and that decimal number and the size of the angle are related. I don't want to get too far into that. We memorize this with a shorthand. I write, and then I remember my little saying, right? Oscar had a hold over Arthur. Remember, the story goes that Oscar the Grouch, you know, from Sesame Street, is chilling in his trash can in his alley off Sesame Street. He's a grouch, right? He does not like people trespassing, and he's kind of aggressive and impulsive. Sweet little Arthur the Aardvark from a different book series. My kids read the books. We didn't watch the show, but I'm pretty sure there's a cartoon of Arthur as well, right? There's Arthur and what's his sister's name? DC. And he has a friend named Francine, and they're all these weird looking animals that behave as people. He's sweet and he's gentle and he wears glasses and he's sometimes he wears a little bow tie, I think. He comes innocently walking down the alley, not realizing that flippin' Oscar is going to have a heart attack if he sees someone in his alley. So, poor Arthur, Oscar jumps out of his trash can. He's not just a puppet, you guys. He really can jump out of the trash can. And he jumps on top of Arthur and he knocks him to the ground and he starts choking him. And so we remember that Oscar had a hold on Arthur. He was choking his neck, you guys. Can't you just see his green fuzzy hands? Here, I'll show it here. His green fuzzy hands are choking Arthur's sleek little brown neck. And Arthur's eyeballs are popping and his glasses got fallen off. I think Arthur's glasses probably are broken. I think Oscar probably tramples them. But this is how I remember these trig functions. It's a somewhat violent image, but you know, that helps me remember it. And P.S., another good thing to know when you're trying to memorize something, if you can introduce some kind of motion, we remember motion. Our memories remember motion better than static images. So if you can introduce some kind of motion into your images, it will help you remember them. That's why I embrace the violence here and just let Oscar choke the crap out of poor Arthur, because it helps me remember. And you know, that's the name of the game, right? My needs are more important than anything else. Okay, so how do we use this? P.S. This is when we need calculators. I like to use a scientific calculator on my phone. That works absolutely well for me. If you would like to use a calculator, that's fine with me too. If it's a graphing calculator, that's cool, but it doesn't need to be. Traditional classroom teachers usually don't let their students use their phones because they're afraid their students are going to cheat and like Google the answer or something. I don't even know. But that's not me. I'm fine with you using your phone, but just know that in most traditional classes, and certainly at Edmonds College, they probably would not want you to do that. Another option is if you're doing your homework and there's a laptop or a desktop handy, you can Google the values. I'm sure there's a way to do it online. I've never done it, but I'm sure that there is. Okay, so example 14.1. Let's see what we got here. We're supposed to find A and B, and we've got a nifty triangle here. It's a right triangle, so we say, oh, thank goodness. Life's going to be okay. A, B. Here's the angle, and we're told this is a 36-degree angle. And then we're also told that the length of the hypotenuse is 6. All right, so we orient ourselves. We're standing here. We see that this is a 36-degree angle. Let's start by trying to figure out what A is. A, we see, is the adjacent side, and we've been given the hypotenuse. We see the hypotenuse is 6. Okay, so to use this one, we're going to say, let's use cosine, because that's the trig function, that's the fraction that, or the ratio that compares adjacent to hypotenuse. Adjacents are mystery, hypotenuse we've got. So the way we write that is the cosine of 36 degrees equals A over 6, right? Cosine, I put in the angle mark, equals the adjacent side, which we're just using A, that's our variable. and then our hypotenuse is 6. Okay, that's how we start this. Then what we do, and very quickly you can start doing this mentally, we can see that the hypotenuse needs to come up and be cross multiplied, right? We need to get that up here so that we're just solving for A. So what you can do when you're writing these problems is you can write the hypotenuse right up here. Again, the idea behind it is that we're cross multiplying, right? A times 1 equals those two. So we write it like this: 6 times the cosine of 36 degrees equals A. Now it's a simple matter of going to your calculator, and we want to work backwards. What you'll do is you'll locate your cosine buttons, and then you'll enter 36, and then you'll hit cosine, and then you'll multiply it times 6. And the answer that you should get, that will give you the value for A, and the value you should get is 4.854, and I think it goes on from there. We're typically going to round to the hundredths place, so we would round this to A equals 4.85. A really important question to get an answer to when you're taking a math class, especially at the college level, is how many decimal places are we supposed to round to? Either ask that or make sure somebody in your class asks that, or make sure your professor tells you, because that makes a big difference. In this class, we're typically going to round to 2, but sometimes we'll round to 3, and sometimes we'll even use 4 decimal places. It's not harder, it's just a little crazier. If you're not sure how many decimal places to use, you can always check the solutions manual. Don't look at the answer, don't look at the steps. Just take a quick glance and see how many decimal places John is working it to. Okay, so this is the length of this side, and now we're ready to find this side. Again, we know, okay, our angle's 36 degrees, our hypotenuse is 6, but this side is our opposite. So we'll want to use the sine function, because sine is the name of the function that relates the opposite to the hypotenuse. By the way, we can call these ratios or fractions, right? They're fractions. They're ratios. We can call them functions. That's kind of a fancy name for them. We can also reduce this fraction to a decimal number. So sometimes people will call this part the decimal as well. Okay, let's do the B. We want to use sine. So we'll say the sine of 36 degrees, right? Because it's still this angle, equals B over 6. And then we'll do the same thing. I'm running quickly out of space. I'm going to go to the other page. I'm really sorry. We're going to take this 6 and we're going to put it up in front just like we did here, right? We'll take this 6 and we'll pop it up. We'll do the same thing here. So 6 times the sine of 36 degrees equals B. 6 times the sine of 36 degrees equals B. Again, once you get the hang of this, you can skip writing it as a fraction, and you can just go right to this form. You can basically do this in your head. And then we go to the calculator, we enter 36, then we hit the sine button, and then we say times 6. And what you should get for B equals, I'm going to give you 3 decimal places, 3.527. Okay? What we do not want to do is find the sine of 36 degrees, round that into a decimal number, and then separately multiply it by 6. We want to keep all those long decimal chains alive in the calculator until the very end of the calculation. Then we round at the end. Sometimes John's rounding will get a little nutty and fall out of alignment with what I calculate, and it's because he'll round in the middle of the calculation. No bueno, don't do that. Just keep all the numbers in your calculator and round at the very end. And this we would round to B equals 3.53 if we wanted to go to 2 decimal places. All right? So there's a great example of how we use trig functions to solve for missing sides, right? That's what we were doing here. We were using trig functions to solve for missing sides. Now, having explained everything and your brain feels really good, I'm going to flip it a little bit, and I'm going to talk about inverse functions. All right, and this is mostly, remember that this is what we're doing. We're doing, say, the sine of theta degrees equals point, I'm just making up numbers here, ABC. Okay, I don't want actual numbers in there. This is the angle, and this is the fraction or ratio rewritten as a decimal. Okay, you know how we started with like, if it's sine, it would be Oscar had, right? If we take those two numbers and divide them, then we'll end up with a decimal, right? So we can take those ratios that we're so familiar with and rewrite them as decimals if we have numbers for both of those. Normally, the buttons that we use on our calculator, calculator, there's one set of buttons that says sine and cosine and tangent, right? They're separate buttons, but they're all right in a row together. Those are the buttons that we use when we know the degree of the angle and we want the decimal number of the ratio. Okay, so we use these buttons when we know this and we want that. But there's another set of buttons. And to get to them on most calculators, you have to press the second key. If you have any confusion about this, I can help you out in video chat. These buttons look a little different. They have a negative exponent of 1. Oh, I'm sorry, this should say cosine. This is tangent. Now, this makes it seem like they're the reciprocal, right? Because -1, an exponent, that changes it to turn it into a reciprocal. But that's not true. So don't overthink this -1. This is how we calculate the inverse function, right? This is the regular calculation. This is how we calculate the inverse. And the inverse is when we know the decimal / ratio, right? Either in fraction or decimal form, and we want the degree of the angle. This is super important because everybody gets confused as to when you use this button versus those buttons, all right? So this is the little list that will help you. It depends on what you know and what you're trying to find out. If you know this and you're trying to find the angle, that's when you use the inverse functions, okay? The example we just did was this kind. We knew the angle and we wanted to figure out the decimal number. All right, so now we're going to do a problem that uses these buttons so that you get a little practice of those too. Ready? But this is super helpful. Make sure you copy this. Pause me if you don't have it all written down because I know I wrote a lot really fast. But this will answer that question of when do I use the regular buttons and when do I use the ones with the little -1 that looks like they should be reciprocals, but they're really not reciprocals. They're really inverse. Okay, ready? Let's do example 14-2. Here comes a cute little triangle. It's a right triangle, thank goodness. It's this. This side we're told is 3. This side is 7. This is x. And this is m degrees. We don't know the degrees. As soon as you notice that, If you're like me, it will give you a little sinking feeling because it's like, dude, I'm used to knowing the degrees. I don't like to not know the degrees of my angle. That makes me uncomfortable. That tells me, aha, I'm going to be needing to use my inverse functions. Okay? So, how do we do that? Well, let's remember, let me get these guys down so we have them in front of us. Oscar had a hold over Arthur. Oh, I think his lenses are cracked in his glasses and his lunch bag got knocked behind a trash can. And I think Francine's coming and she's going to help him, but things are not good for Oscar. Poor guy. I mean, things are not good for Arthur. Oscar needs therapy. Let's be honest, right? He's got some sort of traumatic rage issues. I don't know what to say. Okay, we have to do what we can. We have to use the numbers we've been given to try to solve for m. So here we are. And we see, oh, well, we do have two numbers. Can we build a ratio out of that? I don't know. Let's find out which sides they are relative to us. This is definitely the hypotenuse. And this one would be the opposite, right? This is adjacent down here. So this is what we can write. Let's see, it's opposite over hypotenuse, that sign. So the sine of m degrees equals opposite 3 over 7. Oh, okay. So here's how we do, and you can use your calculator for this. You can't do it otherwise. Well, you can, but I'll tell you a story about that in a minute. This is how you're going to do it. And I'm sorry I can't show you this, but my camera is my calculator. And I should really have a second calculator, but I want to use a phone calculator. I should borrow one of my daughter's phones. I'm sorry. Okay, but I'll help you. First thing you do is you take enter 3 and divide it by 7. That converts the fraction to a decimal number, right? So step 1. Convert fraction to a decimal. Okay, that's why it's a little bit confusing because I'm talking about decimals and you're like, there's no decimals in here. Well, yeah, we can make this into a decimal anytime we want. Now, after you've converted that into a decimal, don't copy the number out or anything like that. Don't round here. Then step 2, you want to hit the second key. And then you want to hit sine to the -1. That answer will be the number of degrees in this angle right here. And what we get is that m equals 25.3, and it looks like this answer's rounded, 25.38 degrees. Oh, that's not so bad, is it? You just have to know how to use this button. And again, we're finding an inverse function because we've got the decimal and we want the angle. So this is the size of the angle of that right there. Cool, right? Does John want us to find x? Yeah, he does. He wants us to find side x as well. Okay, well, we've got lots of options for that. But the easiest one is to use Pythagorean theorem. A squared plus b squared equals c squared. So this is to find m. And this is to find x. And we could do this in either order. It doesn't matter. 3 squared plus x squared equals hypotenuse 7 squared. Yeah? 9 plus x squared equals 49. X squared equals 40. We take the square root. Square root of 40 can be broken down. I can see really quickly it's 4 times 10. 4 is 2 times 2. 10 is 2 times 5. Here's a pair of pigs that we can take out. Remember, 2 pigs in the house equals 1 pig out of the house. And then we're left with those 2. So we're going to get x equals 2 square root of 10. And from that, if you want to, this is a perfectly fine answer for me. John in the book takes this and calculates a decimal value for this. He doesn't want the radical sign. So that is 6.32. But he also got square root of 40. Now, what about the fact, just a second, simplified by calculator. We do not have the capacity to calculate the square root of 10 in our brains, right? We can simplify it, but we can't make that go away. With the calculator, you can. But again, I'm not worried about teaching you how to manipulate your calculator this year. I want you to understand the concepts, and then next year, when you're taking college level math at wherever you're taking it, then you can add, you'll add in more calculator tricks, but that's easy, that's not hard. Calculators distract us from the ideas and the understanding. It happens to me too, you guys. As soon as I get a calculator in my hand, all I'm thinking about is pushing buttons. I'm not thinking about the calculation anymore. I'm just pushing buttons and hoping it works out right. That's why I do not like to use calculators, because they distract us from the real conceptual understanding of what's going on. So I want you to spend your high school years focusing on truly understanding how the calculations work, and then you can go to college and learn how to make the calculations happen faster. Okay, so this is the answer I would prefer to see. When we took the square root here, you could and probably should have said, hey, what about plus or minus? Shouldn't we be considering the negative square root of 40? Well, the fun answer is that when we're in the land of geometry and trigonometry, there's no way that could be a negative value, right? That's what we're finding is the length of this side, right, to find x. This can't be a negative number, so we get to discard negative roots left and right, which I am a fan of. So that is one really fun thing about geometry. Okay, moving on. This lesson is a little bit long, so I apologize for that. One thing I want to make sure that you understand, this is our grid, right? Our Cartesian coordinate system. And this system was developed by seafarers, sailors who were navigating their way across waters. And in their thinking, this line was the horizon line, all right? So they would use their sextants and such, and they would maybe navigate toward a star that was up there. This distance is called the angle of elevation, all right? But then other people using similar work, I want to say surveyors maybe, they might measure down from the horizon, right? They might be standing near a valley and they might be measuring down. This angle is called the angle of depression. Not like anxiety and depression, but just downward. All right, so these are two expressions. We don't hear them a lot, but I want you to be familiar with it. And I want you to really lock back into your brain that this, what we've always called the x-axis up till now, is really important in trigonometry, and we use it as like a horizon line. Okay. Let's try a couple problems that will take that elevation and depression concepts into play. And they're word problems, so it makes everyone a little eked out. I'll read it to you, right? Get your mug of cocoa. A man 6 feet tall is 200 feet from a tree. You don't have to remember anything, just listen to it. And he measures the angle of elevation, this, to the top of the tree as 11 degrees. How tall is the tree? Okay, now I'm going to nitpick this poor guy, but let's draw a picture of what's happening. Here is our dude. He's very skinny. He is 6 feet tall. So from here to here is 6 feet. He spies a tree that he's 200 feet away from a tree. Okay, so here to the tree, and we're saying the middle of the tree too. There's one of my Rembrandt-esque trees. This is 200 feet. He's 200 feet away from the tree, and the angle of elevation from his eyes is 11 degrees. Now, what we're supposed to say is from his eyes, he would look straight across and see the tree like that, right? But he's looking up to the top of the tree, and this is 11 degrees. Does that make sense? He's looking straight across, so that's like his horizon line, right? That's his line, and his angle of elevation from where he looks straight across is 11 degrees, and that reaches to the top of the tree. Interesting, right? Now, the only problem I have with this is that even if he's 6 feet tall, his eyeballs are not at the top of his head. So his eyeballs are not actually 6 feet tall. However, it doesn't really matter for the purposes of this thing, right? Because the 6 feet, that would mean his eyeballs were sitting on the top of his head. That's not where our eyeballs sit. But it doesn't really matter because the 6 feet aren't important. What is important is this triangle. This is 200 feet. I'm adding it here. The adjacent side, if you will. We don't know the hypotenuse. We don't know the opposite side, but we do know that the angle is 11 degrees because it said the angle of elevation. All right? What are we supposed to find? How tall is the tree? Okay, so that 6 feet is going to come into play later, but I'll save my rant for later. All right, so this is how we imagine what's happening. There's how we imagine the triangle. We're supposed to find this. I'm going to call it X. We need to know this side of the tree. Then we'll add it to this part of the tree, which we're supposed to believe is exactly 6 feet tall. Again, that's not quite right, but whatever. We'll round for a few inches from the difference between his eyeballs and the top of his head. It's probably, what, like 3 inches? But this drives me crazy about this problem every single time. Okay, so what we know is that this is the opposite side. And we know that the adjacent side, 200, equals the adjacent side. So we say to but we don't know anything about the hypotenuse. So what we say to ourselves is, gosh, if only there was a trig function that combined opposite and adjacent. And then we say, oh, praise the Lord, there is. Tangent is over Arthur, or on Arthur. It could be over Arthur too. All right. So we're going to use tangent in this one. And what we say is that the tangent of 11 degrees equals, let me just write this here so we have it in front of us, over Arthur. The opposite, which is X, over the adjacent, which is 200. Okay? So we can just use the pieces that we know regarding this triangle to put together a little triggy boy. And then, again, we can bring this up and multiply it. So it would be 200 times the tangent of 11 degrees equals X. Again, enter 11, then hit regular tangent, not the inverse, because in this case we know the degrees and we want the rest of the decimal number. So we're using the regular tangent button. So 11 tangent times 200, and we should get an X value of 33.88. No, 38.88. So that is this distance. But we're supposed to find the distance of the whole tree, so we have to add the 6 feet, right? Because that's the base of the triangle is based on where the man is looking. So the tree is, what's that, 44? 44.88 feet tall, and that's the right answer. All right, you'll probably get a problem like this in the homework. Come back and look at this, and it will make a lot more sense to you. All right, the next one is like this, but it's even trickier. Oh, you're gonna love it, because you know we all love a tricky problem. It's example 14.4. I'll read it to you. An airplane is flying at an altitude of 3,000 feet above the ground. The pilot sights an object on the ground at an angle of depression of 26 degrees. What is the slant range from the airplane to the object? Okay, that doesn't even make sense. But let's take a look at what's happening. Here's our dude in an airplane. I'm not going to pretend to draw an airplane. That would take me a while to do it well. There's our airplane. He is flying at 3,000 feet above the ground. So he's going along like this, right? And he's 3,000 feet above the ground. He looks down and he sees an object on the ground, right? This is the object. And this is the plane. So dude looks down and sees this object on the ground, and the angle of depression is 26 degrees. Right? Okay. And we're supposed to find what is the slant range from the airplane to the object. What they're saying is how long is this distance? Okay. Now, what we want to do is we want to orient our triangle horizontally. We always do that in trig. We always make our triangles go down, and or at least they go to the horizontal line. Sometimes they're going up to the horizontal, but we'll get to that later. But we don't want, this triangle is not going to help us because it's floaty uppy. We want this triangle because it's oriented the way we want it to be. What we're supposed to be finding is this, which I recognize as the hypotenuse of our triangle. So I'm going to call it H. That's the number that John wants us to find. This we know is 300 feet, right? Now, we have to figure out, do we know anything about either one of those angles? Can we possibly orient, can we get a number for either one of these angles so that we can solve this with our calculators? Well, we don't know anything about this one, but look, this makes a right angle, right? And so if this is 26, the total has to be 90. These two are complementary. So this has to be what? 64 degrees. Like so. Oh. Okay, now we've got information about this triangle, which is the one that we want. Pretend that's perfect. Sorry. Now, we just have to orient ourselves up here in order to get that distance, which again, remember I said before, we usually are down here. Here's an exception to my rule. So we can do it, it's just gonna be, we're just gonna have to be careful. So we know the angle, and we know one side, and we need to know the other side. So we have to figure out which sides do we have. Once again, we've got, this is the hypotenuse that we want, and this side is the adjacent. So Oscar had a hold. So this is cosine, right? Cosine is the function that relates a to h. So we can say the cosine of 64 degrees is equal to the adjacent over the hypotenuse. Okay, so that's how we set it up. Now, this one is a little harder to simplify. Normally, if this is the one we don't know and we do know this, we can just bring it up and then enter that all in the computer. This one's going to require a little bit more of an algebraic hoedown. I almost said hoochie coo, a rock and roll hoochie coo. That's an old song. You probably don't know what I'm talking about. These two need to trade places in order to simplify. So we'll say H equals 3,000 over the cosine of 64 degrees. That's how we're going to solve that. Again, we can take it to the calculator. You'll need to enter 3,000. Here, I'll write it down. You'll enter 3,000, then divided by, then parenthesis 64, then the regular cosine function, then the end parenthesis, and then the equals. All right? Hopefully that will help you do it. But we have to use the parentheses for a division problem like this. And what you should get is H equals, because this whole thing is what H is equal to, right? This is just how we put it in. 6843.52 feet. Okay, so experiment with this. If you've got your calculator, pause me right now and make sure that you can get this to work out to that number before you go on any further. And I'm double checking to make sure I didn't copy wrong. All right, if you're having any problems with this calculation, make sure you mention it to me when we video chat this week, because I want to make sure that you're not running into any frustration with this. Okay, so there are some examples of problems we can do using trig functions. Now, that's great, but the vast majority of the time, we're going to be using trig functions. I know this is going on long. Hang on, we're getting close. 2 more problems. Ice cold blood may be flowing through your veins as I write this down. Coordinates. This is something that we use trig functions for a lot. Remember that when we draw our system and choose a point, there are 2 ways that we can basically write in code the location of that point. One thing that we've been doing, instead of calling this X and Y, we've been calling this the right and the up, right? And if you're over here, you're in the positive right. And if you're over here, you're in the negative right. And if you're up here, you're the up. And if you're down here, you're in a negative up position. We can write this in rectangular coordinates, which we do by saying a sign and a number right and a sign and a number up, right? We practice this. Sign and a number. That tells us whether to go to the positive right or the negative right and how far. In this case, it would be there. And then we have another sign and another number, and by sign I mean positive or negative, not sine or cosine. We have another one on the positive, or on the up axis rather, and that gives us a way to find the point that we're talking about. And that's why we call it a rectangular coordinate, because when we're using these to track down our point, we basically draw a rectangle against the grid, right? And that helps us find where the point is. That works great and is very useful in many different situations, but not always. So we also have a thing that we call polar coordinates. And it's a completely different system for locating points on a Cartesian coordinate system. Instead of worrying about the right and the negative right, the up and the negative up, we always start here, and that is 0 degrees. And what we do is we measure the angle from 0 degrees up to the hypotenuse that goes through our point. It would stop right here. Pretend I didn't write all that. Okay, so in these, we have an angle, or what is sometimes called a direction. Okay, so we would write a number inside of this box that represents this angle. Then, outside of the weird little box, we would measure the length of the hypotenuse. And this is what we call the distance. All right? So again, it's another way to find that same point, but first we measure an angle, and then we measure the distance out on that angle to locate our point. These are two equally valid ways to note points on our Cartesian coordinate system. They both have pros and cons, and we'll use them for different things. What is important for us to know is that we will use trig functions to cycle back and forth between the two. We can move from rectangulars to polar or polar to rectangulars using trig functions. So we're going to practice that. We did a lot of this last year, but we'll just practice a little bit. We're converting from one to the other. So in 14.5, let's see what John's got cooked up for us. Convert, and then he gives us some rectangular coordinates, to polar coordinates. Write 4 forms of polar coordinates for this point. Okay, drama, drama, drama. Okay, one thing he does, let me show you the point he gives us. What's this? I's and J's? I said they were R's and U's. Yes, sometimes different mathematicians or different textbook authors will say, oh, I don't want to use R's and U's. I want to use I's and J's. Now, that's a problem, and this is the reason why I don't like this system at all. The reason that's a problem is because we already use lowercase i's, don't we? We use it for imaginary numbers. And honestly, I think that's enough work for that tiny little letter to have to do. It has to represent imaginary numbers, for crying out loud. I don't think we should ask more of it by telling it to be a rectangular coordinate label as well. But it's fine. We can do it if we need to. That's why that little caret is over there, though, that's what that little pointy thing is called, is to say, hey, I'm not an imaginary number. I'm just a weird rectangular coordinate. So as you can tell by the order, I must be this one, and J must be this one. And that's correct. They always are in the proper order. So to find this point, we would go to 1, 2, 3 on the negative I, and then up 2. So that point would be right there, right? To convert a point into a triangle, which is the first step in moving from rectangular to coordinate, we draw the triangle. So I've got my point in. Our triangles always orient to this line. That's what I was trying to say before when I was talking about the airplane problem. We always want to orient to this line. And before it was oriented, that airplane one was trying to make us go upside down. It was a bad scene. But here we go, okay, fine. We'll come out from the origin to the point, and then we'll go straight down, and that makes a nice little right angle. Now, we're supposed to be converting this into, so these we know are rectangular, right? Tangular. So what do we know about this? Well, as a triangle, we know that this side is 3, right? It's not -3, it's 3 units long, and this side is 2 units long. We need to know, in order to write it as a polar coordinate, we need to know this angle and we need to know the hypotenuse. So how can we find those? Let's start by finding the angle. Right? And sometimes it helps me to draw the box for my answer and set the form up the right way. I'm going to need it to be like this, right? I'm going to have the hypotenuse here and the size of the angle there, and this is going to be my polar coordinate. To find the angle, I look at the sides I have, and I realize, oh, that's opposite and that's adjacent. What can I do with that? Tangent will help me. So I'm going to call that theta, which is one of our favorite names for angles we don't know. And we say that the tangent of theta will be equal to over Arthur, so OA, right? Tangent equals OA. So I'll put the opposite 2 over the adjacent 3. Now I can go to my calculator. And first I'll take 2 divided by 3. That will give me 0.667, right? And then I'll enter 0.667. And then because that's the decimals and I want the degrees, I know that what I want is tangent to the -1. And I think you need an equal sign after that. But this is a case where I want my inverse tangent because I know the decimals, which came from the fraction, and I want the degrees. And what I'll find out is that theta is equal to 33.69, right? So that's the size of this angle right here, 33.69 degrees. That's that angle coming out of there. But when we write a polar coordinate, we don't want this angle. For a polar coordinate, we want this angle, right? That's how we use this information. We start at the horizon and we go this way, assuming that it's positive. And that's the measure that we want. So 33.69 is helpful, but it doesn't belong in this box. What we need to put in that box is the full 180 degrees minus the 33.69. Make sense? It's helpful to know what this is, but we don't want that. We want this. So now we subtract, and let's see, this would be a 1, a 3, a 6, and a 4, okay? That tells us that this number is 46.31 degrees. All right? That's cool. We got the angle. Now we have to find the length of the hypotenuse. Now, we could use one of our other trig functions because now we know the angle, blah, blah, blah. We could use a trig function, but we can just use little Pythagorean theorem, right? This is h. I'll call the hypotenuse h. And so we can say that 2 squared plus 3 squared, those are my two legs, equals h squared. So 4 plus 9 equals h squared. That equals 13. And then we take the square root of both sides. So h equals the square root of 13. All right. So there is one form of the answer. All right, but John says he wants us to find 4 forms of the answer. So how could we do that? Let me flip to my next page. Oh, just a second. It's 146, right? When I subtracted here, I forgot to bring the 1 down. So this angle, which makes sense, right? If 46 wouldn't be nearly enough. This angle here is 146.31. All right, so this is my first way of measuring our point, which is roughly out here, right? So now we know that this is square root of 13 and this is 146.13, right? Now what we have to do is play around with some positive negatives. This might have drifted out of your brain over the summer, but in addition to measuring this way, we can also get to this line by measuring this way, right? And so a second form of this would be to say, yeah, we want to go square root of 13, but let's measure the angle this way. Now, in order to do that, well, there's a couple ways we could do it. So let's take the easiest way. I can see that this one plus this one equals a full 360. You see how I'm this and those two measurements should add up to 360. So if I take 360 degrees total and subtract out the 146.13, that should give me the length of the red part. And that would be 78.312. Yes. Now, because we're saying, hey, let's measure in the opposite direction, we have to put a minus sign in front of that. So it's 213.87. So there is a second form of our answer. It's a second form of a polar coordinate that works for this. Now, we can also put a negative sign in front of the hypotenuse, can't we? Lord have mercy. The way that works is that we describe going to this point, right? But then we say minus square root of 13. So what we want to do is we want to give instructions to get to this point, and then we want to say, hey, we're going to reverse it, dudes, and go back the other way. We're going to basically put the car in reverse instead of drive. So we give instructions to go here, but then we say, no, back up instead of go forward. So how do we figure out this blue angle? Well, one way that's helpful is to see that we're going to need 90 plus 90 plus 90 plus this amount is the same as this amount. Do you see that? No, that's not right. This is the same as this amount, right? Because these two are vertical angles. Here, I'll color them in so you can see it better. This guy and this guy are vertical angles. So if we know this bit, then we have to add that on to the 270, right? So I need 90, 180, 270. And then I need to add on this amount. So how much is that? Well, 146 goes that far. So if I subtract, this is crazy, right? Your brain's probably going sideways by now. This total amount is 146.13. So if I subtract 90, that should give me that amount. Okay, so I'm going to say 180 minus 146.13. That should be 7843. Sorry, I'm having an addition drama in my brain. 7 plus 3 is 10. Carry the 1. 1 plus 8 plus 1 is 10. Carry the 1. 4. No, this should be a 3. There we go. Okay? 10, 10, 10. 4 and 4 is 8. Okay. So this amount of the wedge is 33.87. So if I add that to this, that should give me the full direction of the blue. Except I'm off a little bit in my numbers. Let me see. No? Oh. This number should come out to be 326.31. The blue right? Let me come back and find another way to do that. I've gotten a little bit tangled up here. So let's just skip over that. That's the right answer. And I'll come back to it. Let's say for the fourth one, again, we're going to use the negative 13. We're going to use the backup method. But this time, we just need to find the angle like this because we'll use a negative in here as well. So this angle is the same as what we calculated in the first place, right? That's the opposite-y little guy there. So if we go back to our original calculation and find out what we calculated for theta, 33.69, this will be negative 33.69. Does that make sense? Now, another way that we can find this blue number is to say the whole circle, 360, minus this little orange bit, which is 33.69. That should equal the blue part, right? Because the blue and the oranges, there's the orange way out there. The blue and the orange should make a full 360. So let's subtract. 1, 3, 6. Let's see if I got that one right. Oh yeah, there it is. This is the number that goes right there. So I proved it this way. Something went slightly, I think something went slightly wrong in my calculation. I don't want to waste any more time on that because it's just frying your mind. But what I want you to see is that this is how we come up with the 4 different forms of the polar coordinates to reach this place. You find the first one by taking the positive values of both, the easiest way that we learned to do it. And then you start playing, first you take the negative, right? We did the red one next by going backwards. Then we had to put a negative on our hypotenuse and find those 2 angles, all right? So that is something that this is all very useful for, these trig equations. And now we have one more problem. This is a really long lesson, I'm sorry. I hope it's bringing back all kinds of wonderful memories. Convert this number to rectangular form. This is example 14.6. Minus 253 degrees. Okay, so the first thing we always do is draw the triangle. So what we do is we go minus 253 degrees. Boy, what does that look like? that means we start here. We go 90, 180, okay, 270, so we're not going to go the whole way. This much is 180. So let's subtract 180 and see how many we need this way. 373 degrees. So we're talking about like this, right? This would be, this much is 273, no, 253, sorry, degrees. But we don't want to go forward. We want to put the car in reverse at this point. Right? So this is where we thought we wanted to go, and we know that this much is 73 degrees, right? Because it's 180 plus 73 gets us the 253. Then we're backing up that far, and this is 13. So our triangle, that's the hypotenuse. I wish I would have written it over here. I'll write equals h. Now, then we have to figure out, well, how much would that angle be? 73. Then we see, okay, these are opposite each other. So this angle is also 73 degrees. Oh, okay. So now we're trying to go, we've got our triangle drawn, and we can use trig functions to solve for, this is what we would call the adjacent, and this side would be the opposite, right? The hypotenuse is over here. My drawing's a little confusing. All right, so we'll say the cosine of 73 degrees equals the adjacent over 13, because that is our hypotenuse. 13 times the cosine of 73 degrees equals A. And when you run that through your calculator, you'll get, oh, I'm using a lowercase a. It's fine. A equals 3.80. So the length here is A. Now, notice that this is the r-axis, and whenever we're working with triangles and trying to go from polar back to rectangular, if we use cosine first, that will always give us the right measurement. The up measurement, which in this case it's a negative up, that one is always going to be the opposite side, and so up relates to sine. So it makes a lot of sense if you always use cosine first and then sine, because then you'll get the values in the order you want to write them in your answer. The sine of 73 degrees equals O over 13. 13 is our hypotenuse, so we're good. So again, we cross multiply it, and we get 13 times the sine of 73 degrees equals O. And you run that through your calculator, and you get, John called these A and B, but you don't have to do it that way. I prefer to call them adjacent and opposite because that helps me stay oriented to my trig functions. All right, so the opposite side we got is 12.43. So our final step is to write these as rectangular coordinates. And we have to figure out the pluses and minuses for ourselves. We see that our point here has a positive right value, but a negative up value. So I'm going to write plus 3.80r minus 12.43 to the up. That's what I say is my final answer. And I feel good about it, but when I look at John's, I see that this is what he's got for an answer. So I look and see, what did he do differently? Well, he didn't put a plus sign, but that doesn't matter. I used the right and the up. He used the I and the J format. Okay, he's just using the different letters to describe the two axes. It doesn't matter. He's using the little caret. He even used a caret here this time to remind me that he doesn't mean the imaginary number. But again, I don't like that way. I prefer this way. So I would like to keep using that. And I recognize that our two answers are the same. Okay, guess what? Woo! That was a long problem, wasn't it? I'm going to straighten up my math on this blue version, and I will get back to you at the beginning of next lesson and let you know what I did wrong. But I hope you remember that we were able to find the right answer through, we figured out this one, and then we used that one to help us find the blue one. But I'm going to figure out what I was doing wrong there and get back to you. You know what? You deserve a break. Go do something fun. Okay, bye.